first, we're going to talk about a couple features of graphs. If I ask about continuity, or where is a graph continuous? Continuous just means you can draw it without picking up your pencil. So if you can sketch a graph and you have to pick up your pencil somewhere, that's called a discontinuity, or it's a break in our graph. If we could draw the whole thing without picking up a nice smooth curve, that would be continuous. So for instance, if I'm looking at something like this, that's a continuous function. Okay, I can draw the whole thing without picking up my pencil. If I give you something like this, is that continuous? No. We would say that is discontinuous at x equals 0. There's a break in our graph there. It's continuous everywhere except the 0. So let's look at some graphs. And I went too side, sorry. I go too fast. Tell me to slow down if I change slides too quickly. So let's look at some graphs and tell where they are continuous. And I apologize on A. This is supposed to be an open circle right here, but when it graphed over the tick mark, it kind of looked like it was closed. So, is this one continuous everywhere? Can I draw this entire thing without picking up my pencil? We draw, but when I get to the open circle, we have to essentially jump over that point and then keep going. So it's not continuous everywhere. We can give intervals where it's continuous. We use the x values for that, just like when we're talking about increasing and decreasing. The only time you use a y value is if you were talking about the range of a graph. So we could say this is continuous from negative infinity until x is equal to what number? 0. So it's continuous from negative infinity to 0, union 0 to infinity. It's everywhere except the 0. If I look at B, can I draw this whole thing without picking up my pencil? Where did I have to pick up my pencil at? There's no open circle, so we're going zigzag. Do we have to pick up our pencil though? There's no breaks in the graph. We didn't jump from one piece to the next, so this one's continuous everywhere. So it would be negative infinity to positive infinity. C. Is this one continuous everywhere? No, because I have that open circle on my graph. So where would I say this is continuous? Union and D, where is this one continuous? There's no breaks in that graph, it's continuous everywhere. There. The other features with our graphs that we're going to mention are increasing, decreasing, and constant. Increasing means you have a graph that is rising from left to right. So just like with lines, if I say a line is increasing, That means it has a positive slope. Okay, it can be any type of function. As long as it is rising the whole time, that's increasing. Decreasing is falling as you go from left to right. And constant is no change, so that would be like a horizontal line. I may ask you to tell me intervals where certain graphs are increasing, decreasing, or constant. When you do that, you have to give me the x values. The only time we use the y in our intervals is if we are talking about range. Otherwise, we're always using x because if it's a function, there's only one time on the graph that we hit each individual x value. So, we're going to go ahead and start graphing some of our common functions, and then I may ask you some questions about them after we do that. Identity function. That's just f of x equals x, or f of x is the same as what variable? Y. Y equals x, we should know what that is. It's just a line. What's your y-intercept? 0. Slope is 1, so up 1 over 1. And you can get your so this is our identity function. Can you tell me the domain of that function? The range? Is this one increasing, decreasing, or constant? Yeah, it's increasing the entire time. Negative, infinity, positive. All right. Let's talk about the next. F of x equals x squared. F of x is the same as y. When we graph these, so we don't have a graphing calculator to rely on, my general rule is if you are drawing me a graph, I'm going to require a minimum of 3 exact points. So if I want to get some exact points, what could I do? We always get plug numbers in for x, exactly. You can write them down if you need to. We might, the first couple times we graph them, but we will do the same function so often I probably won't make this t-chart every time. So it's fine if you want to do it in your head. If you put in 0, 0 squared is 0. All right, if I put in 1, 1 squared. If I put in 2, 2 squared. If I put in negative 1, negative 1 squared. If I put in negative 2, negative 2 squared. If you wanted to, you could do 3 squared is 9, negative 3 squared is 9. So we're getting a parabola. Remember, when you graph those parabolas, make sure it's more like a U, not a V. Okay, so it's curved there at the bottom. So anytime I ask you to graph x squared, I'm expecting at least 3 exact points, but you can certainly do more. Does everyone understand how I got my exact points? I take the x's and I plug them into the equation x squared to get my y's. What's the domain? Range. What y values do we hit? And why did I put a bracket on my 0? 0 is included. If it's equal to that point, you get a bracket. If I asked, can you tell me, where is this function increasing?
From 0 to infinity.
Technically, with increasing and decreasing, it doesn't matter if you do parentheses or brackets. Because the way it's defined at a single point, you're not going up or down, so either of those would be fine. Where is this graph decreasing? So again, I don't care if you put a parenthesis or a bracket on the 0. Alright. Let's try another one then. So these are all common functions that I'm expecting you to kind of learn what their shapes are like. Now, I'm not expecting you to memorize domain, range, increasing, decreasing. That would be a lot. But if I say x squared, I'm expecting that you could get some points on this graph, and you could look at that graph and answer any other questions I might ask about it. Alright? So the next one, x cubed. So if I want to get exact points, what do we do? Your t-chart. Again, once you get more comfortable with it, you don't necessarily have to write out the t-chart, but that's what you're thinking in your head. So we're going to put in some points, some positives, some negatives, and 0. And I'm putting them into my equation, x cubed. So 0 cubed is 1 cubed is 2 cubed. Negative 1 cubed. Almost. Negative. Negative 1 times negative 1 is positive 1 times another negative will give you a negative. Negative 2 to the third. Here's my graph. My x cubed kind of looks like a chair. Domain. As we go from left to right, what x's does this hit? What y's do we hit? Is this graph increasing, decreasing, or constant? Increasing the entire time. Is that okay? Alright, I really want to make sure everyone knows where I'm getting all this stuff from. Know how I'm getting my exact points. You could get those exact points and draw it yourself if you needed to. Okay, next one we're going to be looking at is the square root function. Okay, so the square root of x. Again, if I want to graph it, I'm going to make my t-chart. If I put in 0, what is the square root of 0? If I put in 1, what is the square root of 1? Can I do the square root of 2? 3? No, they're not nice numbers. What about 4? Square root of 4 would be 2. What's another nice number? Square root of 9 would be 3. Can I do negatives? No, that would give me imaginaries, and we're not graphing those. So this one starts at 0.
So that's what that graph was on that study guide, or on the test
Mhm.
that they had to score.
Yep. Can you tell me the domain of that? like left to right, what x's do we hit? We start at 0, go forever in the positive direction. Range is asking about my y's, so if we start at the bottom, get 0 to questions on that one?
You can't put increasing.
We could. So what is this one doing? It's increasing. Where does it start? And goes to infinity. I want you guys to take a few minutes and see if you can figure out for the cube root, what would your points be on the graph? So if you put in 0, what's the cube root of 0? What is the cube root of 1? Okay, does the cube root of 2 give you a nice answer? No. So what what x did you plug in next? The cube root of 8 is 2. So 8, 2. Can you do cube roots of negative numbers?
Yeah.
Yes. Cube root of negative 1 is cube root of negative 8 is my domain, as we go from left to right, what x's do we hit? And our range? Is this graph increasing, decreasing, or constant? Increasing, it's rising the entire time. Graph the next one. So absolute value tells you how far something is from 0. It essentially just makes any number positive. So you might remember the x squared and the absolute value, I think, were the ones you used the most in Algebra 2. So it might be familiar to you. Otherwise, if you made your t-chart, absolute value of 0 is 0, 1, 1, 2, 2. But if you put in the negatives, they become positive. Now this one is a V. So make sure when you're graphing a parabola, that is like a U. So it's curved at the bottom. Absolute value is a V. It does have that sharp corner. What's the domain of this? And what is your range? Increasing, decreasing, constant. What does this graph do first? And then after 0, what does it do? Increases starting at 0 and going to infinity. Alright, and again, it wouldn't matter if you did a parenthesis or a bracket on the 0. Alright. I'm going to do probably 2 more slides and then I'm stopping for the day. The next one, x equals y squared. So if I ask you to graph this, is it going to be easier to plug in numbers for x or for y? The y. Because we have to square the y. Okay, so we're still making our t-chart, but this time we're doing it the opposite, because if we square that, we get our x out. The y is the variable we're doing something to. 0 squared, 1 squared, 2 squared, negative 1 squared, negative 2 squared. So my points. 0, 0, 1, 1, 4, 2, getting this time? What's that graph? It's like a sideways parabola. If you think about our x squared function, I just flipped my variables x and y, which basically flipped my parabola on its side. Is that one a function?
No,
No. Why?
you haven't passed the line test.
So we can graph non-functions. We're just plugging in our variables for the y instead of the x. Any questions about that? Last thing, I'm just going to set us up for tomorrow. Tomorrow our focus is going to be on symmetry the entire time, so I just want to kind of talk about what symmetry is today. Then tomorrow I'll pick up there and we'll actually do examples and look at the whole thing. So symmetry, you know, probably learned in elementary art class. A line of symmetry is like a line you can fold it over and it overlaps itself, right? When we're looking at graphs, we have three different kinds of symmetry that might happen. Something could be symmetric to the y-axis. So that means if I fold it over the y-axis, it overlaps itself. A good example might be like a parabola. Okay, would you agree that if you folded that on your vertical line, your y-axis, it would overlap? The two sides are the same. In terms of that, and this is what we're really going to focus on tomorrow, when you're looking at your points, when the x is positive or negative, it has the same y value. You know, if we look back when we graphed our parabola, a positive x and a negative x gave us the same y. Positive 2, negative 2 gave us the same y. So when something is symmetric over the y-axis, both a positive and negative x are equal to the same y value. If something is symmetric to the x, that might be the example we just did, that sideways parabola. That means if we flip this thing over the x-axis, it overlaps itself. If we look at that point, a positive and negative y give us the same thing. When y is 1 and negative 1, we get the same x. When y is 2 and negative 2, we get the same x. So if it's symmetric to the y, positive and negative y are equal to the same x. The third type is symmetric to the origin. This is the one that's a little bit different. So origin basically requires you to flip over both the x and the y-axis. So it would be something like our x cubed. If I flip this over the y, then take that and flip it over the x, it overlaps itself. Do you guys see what I mean by that? So it takes two flips. If you're looking at your points, they're total opposites. And this is positive 1, positive 1. This is negative 1, negative 1. You have to change both the x and the y. Change signs when you do that. So that's where we will pick up tomorrow, really going into that symmetry piece. Today, there is a handout posted on Google Classroom that you should be able to do. It shouldn't take you too terribly long. So you might be able to get that done before class is out. Somebody, is there still one back there? Someone left. You're welcome to use it while you're in there.